Hi, my name is Loris Crow, and we are executing at Showtime. Zig Showtime is the show where members of the Zig community come on stream to share coded ideas with the broader public. Every episode features two speakers who will present and take questions from you, the viewers. Zig Showtime is not just what you're seeing on the live stream, but also the discussions that you can have while watching, and that's why I encourage you to join one of the existing Zig communities that you can find by going to zigland.org. So, hello, episode 15, I think. By the way, I always do the same introduction where I tell people to go and check out one of the Z communities. But also, I've seen that recently people have started like grouping together in like a Discord voice channel to do like a watch party, I guess, of some kind. So if you're into this kind of stuff, really go check it out. I think it's an interesting way of experiencing shows like Zig Showtime and in general. I think new things that you can do with online communities that you wouldn't be able to do in the past, or at least, not as naturally. Let's moving forward. Let's talk about news. I think the main news for now is that we are about to we're approaching the release of Z version 0.7.0. As you heard, it's going to be next week, and we're going to have a release party on Showtime. So next Showtime, we will not have any regular talk, but it's going to be me, Andrew, and I don't know, maybe someone else, if we can figure out something, if we can convince other people to join and have something interesting to do with them. But in general, it's going to be just to celebrate the new version. Maybe we'll take a peek at the change logs, answer some questions. So just some fun, some relaxation time, I guess. So with that said, let's move to the first talk. So let me switch the scene and we prepare for a moment so I can read the intro. Okay, so okay. If you're watching this talk, you probably know Frank from his work on Libsodium. But before that, Frank was and is a photographer. And I think I'm not saying anything surprising by pointing out that to be a photographer, you need to have a mind particularly sensitive to elegance and beauty, which maybe explains his interest in crypto, and which definitely explains his interest in Zig. So, the title is a tour of std.crypto in Zig 0.7.0. Frank, the stream is yours.
Hello, everyone. So, hope you're as excited as I am about the forthcoming release of Zig 0.7.0. There's been so many changes. I haven't been able to keep up with all the changes. So really have been focused on just one thing, which is the std crypto directory. I've been somehow able to follow that one. So this is what we're going to talk about today. So what is std.crypto? What can you find in here?
Frank, sorry to interrupt you.
Essentially,
I think we need to restart the video stream. For some reason, it's all black.
Oh, okay.
Give me a second. I'll try to do it. Okay, now it works. Now we see the title, Zig for cryptography.
Okay.
std crypto.
And
okay, sorry.
Next slide as well?
Now it's working. Yeah, apologies.
Oh, okay, perfect. Anyway, you didn't miss anything important. So std.crypto, what is it? What can we find? Well, crypto APIs. Crypto APIs doesn't mean anything because, if you take a look around, look at existing crypto APIs, there are many, many kind of APIs you can find. For example, some of them, right in the middle, provide constructions and primitives, things for hashing or encryption, signatures. This is probably the most common kind of crypto libraries, and so APIs that you can find. But also, on top of this kind of APIs, you can find protocols. And when I say protocols, this is not just network protocols. It could be a file format to encrypt files. It could be TLS. It could be a specific blockchain. So all these high-level APIs are built on top of what's in the middle, on top of constructions and primitives. So different set of APIs. And at the very bottom, we have a bunch of foundations, such as being able to do finite field arithmetic or even hardware abstractions. Still, a different kind of APIs. So where do we stand? What do we have in Zig? Well, let's take a look at what we actually have in std.crypto. Since Zig 0.7, everything has been organized into a bunch of categories. So we can take a look at one of them, which is core. And core is pretty interesting because if you just use it alone, it's pretty much useless. So let's take a look. For example, you're going to find things such as AES, Gimli, and mods. So AES may sound familiar. So let's take a look at AES. What is AES, by the way? AES is just a permutation. So you take a set of numbers, actually a list. This is what you have on the left. And you just shuffle that list in a pretty messy way. You get the list on the right. And AES is pretty much this kind of map function that maps what's on the left to what you get on the right. And if you perform exactly the same steps, but in reverse, you can go from the right back to the left. This is a permutation. And AES is pretty much exactly that, except that instead of having just 10 elements, you have a little bit more. We have blocks of 128 bits. So that's bigger, but it's still deterministic. You can go from the left to the right and the other way around. This is all what the AES core function does, nothing else. So AES was really designed for hardware implementations. If you try to implement AES in software, it may be insecure due to side channels. And if you want to implement mitigations against side channels, well, they have a cost. And then it's going to be slow. This is not great, right? So what can we do? Well, modern CPUs have dedicated instruction sets for AES. For example, on Intel, we have the ASNI instruction set. And on ARM CPUs, we have ARM crypto extensions, which provide a bunch of interesting things, including AES functions. So great. However, this requires using intrinsics or assembly code. Even in Zig, this is not something we can do directly. Plus, even if these instructions look similar, they're not really the same. They have to be used differently to achieve the same result. So it's a little bit annoying if you want something portable and easy to use. Anyway, so if you use hardware instructions for AES, maybe you're going to be fast and secure. Well, not quite. Let me tell you why. Well, you could go way faster, actually, because modern CPUs are fast, if only because they have executions pipelines. They can start processing an instruction before the previous one is even done. So if we take a look at the AES instruction, this is on Intel. AES Inc. just encrypts an AES block. And on this specific CPU, this instruction has a latency of 4 clock cycles, which means that when you start this instruction, it's going to take 4 cycles before you get the result. So you can compute whatever you need to provide to this instruction, run it, get what you need for the next round, and do it again and again in a very sequential way. Or what you can do is prepare everything for a couple calls of this instruction, and then performs many calls in a row. So on this CPU, we have a latency of 4, but a throughput of 1, which means that we can schedule a new one, just 1 cycle after the previous one, even if the previous one is not done yet. So, and you can see here, if we do 4 AES encryption instead of 1, and then another one, and then another one, and then another one, it's way faster. So having a multiple of 4 blocks sounds pretty nice, quite faster. So parallelism is important. And on that CPU, which is AMD Zen and Zen 2, we actually have 2 execution pipelines. So we probably should run 8 AES encryption at the same time to get optimal throughput. So it's nice, but it's very hardware specific. For example, here I've been talking about 2 execution pipelines. So 8 is a nice number to choose for parallelism, but is it some kind of magic number that works everywhere? Well, not quite. If you take a look at the Zig source code, you're gonna see something like this. We actually expose the optimal number of blocks to use for different models of CPUs. This list is not extensive, but still it's useful. Also, we have a parallel version of the AES API, so you can send a vector and it's going to do AES encryption as fast as possible by leveraging parallelism. So cool, this is something we can do easily in Zig. What can we do with that? Well, imagine you have a secret, we run this AES function, and then we get the secret encrypted. Sounds easy, right? Well, just to be sure, to be really secure, we can run this AES function a couple times. There's an intuition that if we run it more than once, it might be more secure, and it actually is. However, remember that AES is a permutation, and a permutation can be reversed. You can execute the same steps in reverse. And even if you have 1 million iteration of this AES function, this scheme is completely insecure. It doesn't provide any kind of security whatsoever, even if it says AES. All right. So this is something we can fix. For example, instead of having our secrets directly on the top, what we can do is expand this secret into multiple secrets. And then we add these secrets. So this weird symbol in the middle of each arrows is technically an addition. You can see that as XOR in practice. So we just mix a secret or a part of the secret between each round of the AES function. Why do we do that? Well, if you start from the bottom and your goal is to go up to the initial secret or to recover all the secrets, well, you can try to go up, but if you don't know secret underscore 5 here, when you reverse the permutation, all you're gonna get is something that doesn't make any sense, and this is not the real output of the previous iteration. So having this intermediate secret is what makes the scheme actually secure. And the higher you have to get, the more secure you will be. This is a more realistic way to use AES, because with the previous scheme, we were able to encrypt a secret, and that's it. In practice, what you usually want to do is have a key and then use that key to encrypt multiple things. So we do pretty much exactly the same thing as on the previous slide. We start from the key, we expand this key into multiple subkeys. They are called round keys. And we don't have 5 of them. In practice, we have between 10 and 14 of them. And we do exactly the same thing as before. We add each round key between each round. So what do we have at the top? Well, I just wrote something, because it could be anything. It could be a secret message that you want to encrypt, or it could be something absolutely not secret. But no matter what you have, at the end, at the very bottom, what you're gonna get is deterministic gibberish. It looks like completely random. However, if you know the key for a given something and a given key, it's gonna be exactly the same thing every time. So what we just built right here is called a block cipher. And having to apply each key between each round, it's called a key schedule. If you take a look at the Zig source code, you're gonna see a type called key schedule. And this type is able to compute all the intermediate round key that you can see here. And if you want to do this whole thing, do the key expansion and then run multiple runs, and then you get this gibberish, you have two very simple functions, AS encrypt and AS decrypt. The second one does exactly the same thing, just in reverse. Very cool. However, so far, what we can do is encrypt 16 bytes. I mean, it's okay. It's not too bad. There is some satisfaction here, but it's a little bit lame. We may want to encrypt more. So what can we do? Well, there are different things we could do, and these things are called mods. One of them is very simple and intuitive. The input, the something that we had, I don't know, 3 slides before, the something can be just a block number. So we're going to split the message into multiple blocks of 16 bytes. And then the input is going to be block 1, block number 2, block number 3, just the block number. We're going to apply exactly the same key schedule every time. But because we have a different input, the output for every single block is going to be completely different. So we're going to get gibberish, but completely different gibberish if we have 1 as an input or if we have 2. So if we combine this gibberish with each message block, we get the message, but encrypted. One pretty nice thing about this scheme is the fact that it's easy to vectorize. Because we use exactly the same key schedule, we can encrypt 4 or 8 or 7 blocks at the same time. And remember that if you process multiple blocks at the same time, it can be faster because you can leverage what modern CPUs can do. So this specific mode is used a lot nowadays because it's fast. So if you want to use a mod, Zig got you covered. You have something in core, because we are looking at core right now, called mods. And in mods, you can find CTR, which implements counter mode. Great. So we can encrypt a message of any length now. Awesome. Are we secure yet? Well, not really. Remember that we got this gibberish, and then we just XOR this gibberish with a message. So an attacker can flip a bit in the ciphertext, and it's going to flip the same bit in the message. And there is no way we can detect that the message has been tampered with. This is slightly annoying. So how to fix that? Introducing MACs. So a MAC, a message authentication code, is a very simple function that takes a message and a key, and it returns a tag, authentication tag. Essentially, if you know the key, you can compute a tag for any message. But also, if you are sent a message and a tag, and you know the key, you can recompute the key and verify that the tag that you got matches the one that you computed. If it's the case, the message hasn't been tampered with. If there's a mismatch, you should just ignore the message. Something wrong happened. And if an attacker doesn't know okay, there's nothing they can do. They can't compute any valid message for the tag, and they can't change the message and compute a valid tag either. So in Zig, MACs are available as crypto.auth.something and also crypto one-time auth. What's the difference, you may ask? Well, in the second case, one-time auth, we are dealing with what's called universal hash functions. These functions can be really fast, and they also have some interesting properties. But the downside is that a key has to be used only once. If you reuse a key with 2 different messages, an attacker can compute a valid tag for a different message, which kind of defeats the whole purpose of a MAC. So the second category is super interesting, quite fast, quite common, but it can be tricky to use correctly. Change the key every time you want to authenticate a new message. Okay, so far we know how to encrypt a message of any length. Nice. We know how to compute something to detect if a message has been tampered with. we can combine both, and then we get what's called authenticated encryption. This is cool. Now you want to send this to another party. Maybe you want to add some non-secret information. For example, a protocol version, which can be useful to know what kind of cipher has been used to encrypt the message. So this is something you don't want to be encrypted, but this is something also that you don't want a third party to be able to change. For an example of why this is bad, take a look at JWT. This is terrible. You can change the kind of encryption, and there's no way to detect that it happened, and it's catastrophic. Don't get me started on JWT. So what you can do to prevent that is when you compute the tag to include this extra data, this non-encrypted data, in this case, the protocol version in the computation. So this is called either additional data or associated data. You can find both. I tend to say additional, but both are okay. So you compute this tag, which is going to authenticate both the message or the ciphertext that represents the same thing and some non-secret data. And you send everything, this additional data on the clear, the ciphertext, and the tag to some recipient. You just built what's called an ahead. So authenticated encryption with additional data. Awesome. Are we secure yet? Not really. If you send the same message twice, the ciphertext and the tag actually will be exactly the same. And maybe this is not something you want to disclose. And remember that for some Macs, you shouldn't use the same key twice. And that will be the key, the case. So introducing nonces. Whew. So a nonce is just a number that you should use only once. And if you encrypt something using a nonce, you get some ciphertext and tag. And if you change the nonce, even just one bit, well, you get a completely different ciphertext and tag. So cool, problem solved. Now, if you encrypt the same message twice, you get completely different output. So what can you use as a nonce? A counter might work. It might not repeat too fast. However, you have to keep states. Can be tricky. Maybe you can use a random nonce, which can be okay, except that if the size of a nonce is pretty small, you need to switch to a new key before you get a collision. So in some protocols, this is okay. In some other protocols, there's some overhead, and you have more things to design and implement. So the nonce size is an important parameter. Anyway, are we secure yet? Not really, because we should use different keys for authentication and encryption. Well, first, this is good hygiene, and then maybe they must have a different size. So, well, we need something that takes one key and derives two keys out of it. Yeah, that's a lot already. So just some takeaways so far. First, if a product says, hey, it uses AES-256, well, it doesn't mean anything. In particular, it doesn't mean that it's secure. If you don't get any additional information, it's probably snake oil cryptography, especially if it says military grade. So is there a way to do everything we've been discussing so far in a very simple way using standard constructions? Yeah, absolutely. So in Zig, you have something in crypto.ahead. We have actually a bunch of constructions exposing the same set of APIs with two interesting functions, encrypt and decrypt. Encrypt takes a message, additional data, which can be empty, a nonce, a key, and boom, you get the ciphertext and a tag. And decrypt does the opposite operation and verifies that the tag is valid. Cool, much, much, much easier to use, right? Cool, so what do we have in crypto.ahead exactly? We have something called ASGCM. You can use it if compliance is a priority for you. It's a pretty old construction, but it's still okay. Nonces are small, which is okay for TLS because TLS includes everything you need to negotiate a new key over an existing connection. But if you re-implement your own protocol, it can be a little bit lousy to use correctly. AES-GCM is fast if you have AES acceleration. So it's fast on recent CPUs, but on non-Intel, non-ARM CPUs without acceleration, it can be slow and or insecure. CHACHA 20 Poly 1305. So this is a pretty new construction. If you use TLS 1.3, and you probably do, you are aware of it. So it's a nice construction. It has nonce which can be the same size as AES-GCM, or it could be pretty large. And this is interesting. This is an extended version of this construction, which is being standardized right now. And with this pretty large nonce, you can pick nonces using a random number generator, and you will never ever get a collision, which is super cool. It's also faster than AES-GCM and safer. So if you don't have AES acceleration, this is a good choice. We have a variant called X-Salsa with pretty much the same properties. I'm going to talk about it later. Edges. This is a very new construction. It's been explicitly designed for modern CPUs with ASNI. It's super, super, super fast. So I don't want to spoil it. If you want to have some fun, you can run the benchmark that you can find in std.crypto. It's super fast on Intel, but also on ARM. Even the software implementation is super fast. It's actually more secure than AES-GCM, especially due to the GCM part of AES-GCM, and way faster. Plus, it has a large nonce, a really large nonce if you use the 256 version, which is nice. So you can not only pick nonces at random, but also include additional information in the nonce itself, such as a packet number or whatever. This is a really, really cool cipher. Gimli is very small, lightweight. The performance is not that great, but it's consistent across all platforms. Okay, so where do the Zig crypto APIs fit? So as we just saw right here, we don't provide any kind of high-level protocols, but we provide not only foundations, you have direct access to the AES permutation, for example, but we also provide ready-to-use constructions. Why do we expose low-level APIs? Well, one of the reasons is that you can implement new cryptography easily. You can leverage what we have, such as hardware abstractions, very easily in pure Zig. And this is really nice. If we didn't have edges, for example, this is something we could implement without having to use assembly or whatever. Why don't we implement protocol? The highest level of APIs. Well, most of them are really domain specific. If you want to implement a blockchain or if you want to just do file encryption, you probably don't want the same kind of APIs. Plus, you have to pick specific constructions and file formats and network protocols and encoding formats and what's not. So these things are really opinionated, and this is probably not something that we want to see in the standard library. They are better implemented as external packages. However, we provide all the building blocks so that you can implement these protocols easily and securely. All right, so back to our little tour of std crypto. Crypto.hash, nothing really surprising here. Hash functions. A hash function takes a message and returns something of a fixed length. If you get a hash, finding a message giving this hash is hard. Finding a different message producing the same hash is hard. Finding a collision is hard too, even for quantum computers. Great. So I just said that a hash function is something that takes a message and return a digest. Well, this
I think we lost Frank. uh, okay, people in chat, can you confirm that I'm still alive? I should be, I think. I don't see drop frames. Let me see. Yeah, I don't have drop frames, so I think we lost Frank. Okay, let's give him a second to come back. That's the problem of having everyone.
parameters.
Okay, Frank.
Yeah.
Sorry.
Yeah.
You got cut off for like I think 10 to 15 seconds completely. So
Okay.
let me see if the streaming is still alive. Yes. So we lost you briefly when you were saying that hashes have a fixed length, and then you were about to say that that's not good enough, I guess.
Oh, okay. Okay. So I can do it again. No worries.
Sorry.
Okay. So sorry, people. Apparently, we got cut a little bit. No worries. So a hash function being defined as something that takes a message and return a fixed length digest is okay, but it's a little bit of a traditional definition, and it doesn't really match modern hash functions that can do much, much more. For example, modern hash functions can spit out a digest of any length or of a length between some range. In addition to that, modern hash functions can accept an optional key and a context. They can leverage multiple cores, so you can also specify a number of threads, and so on and so forth. And according to the function you use, the set of available parameters can vary. So we need to provide a modern API that adjusts to modern functions, which is why, and it might be surprising at first, you can see that when you use a hash function in Zig, this initialization function requires a set, which is empty here, but this is a set of parameters. And the actual set of parameters depend on what primitive you choose. For example, for Blake2B here, we could easily add a key, a context, a thought, everything that Blake2 has to offer. This is supported in Zig right now. You just have to pass it as an option. And something important in the Zig crypto APIs is that within the same family of function, the APIs are the same, which is why even for hash functions such as SHA1 or MD5 that don't support parameters, you still have to use an empty set just for consistency. So this is what we have for hash functions. One which is pretty interesting and that you will probably recognize is Gimli. Gimli can be used both for encryption and for hashing. If you want to minimize the memory usage and storage, you can use Gimli for both operations. It's not super fast, but if you're looking for something very small, it's a good choice. Blake 3 is eventually the one who's going to be super, super fast. Right now, it's not as fast as it could be. There's a lot of room for optimizations, but this will eventually happen, and you won't have to change anything to your code to gain speed from this optimization. Just recompile with a newer version of Zig, and boom. Just a warning, there is something called zip hash, and zip hash is not a hash function, in spite of the name. This is actually a MAC, because if you know the key, it's easy to compute an input that will produce this a specific result. So it's not collision resistant. So this specific function was specifically designed for hash maps. For example, for a hash map, if the input is not trusted, an attacker can craft specific input so that everything ends up in the same bucket. And then your hash map is going to be super slow. So if you use zip hash with some secret key, it's going to be much harder for an attacker to actually target a specific bucket. The same thing applies to Bloom filters, count, min, sketch, and all these structures requiring some hash functions. So this is why cPash is not in crypto.hash, but it's in crypto.auth. Remember that a little bit before, we had to derive two keys from one. This is what you can do with what's in crypto.kdf. You can see an example on the top. You start from a key, and that key can have any lengths. And all the bits don't even have to be uniform. And from here, you extract a key, which is PRK in this case, and then using this PRK, you can compute any number of subkeys. The second parameter is just a description. This is what you're going to use the key for, and boom, you can have as many keys as you want, starting with just one key. Cool. CryptoStream, you just pass a secret key, a nonce, and you get a deterministic stream of gibberish. This is pretty much what we built with the block cipher and the counter mode before, except that it doesn't have to be a block cipher to build this kind of construction. Let's switch to something a little bit more interesting and talk about passwords. Passwords are leaked all the time. And this is not always because websites are hacked. For example, an employee can make a dump of the database with all the customer accounts before they leave the company. And leaks happen so frequently that if you don't know this website, haveibeenpwned.com, check it out as soon as possible. You will be scared. And a common practice is to hash passwords before storing them. Using regular hash functions is quite common, especially if you take a look at the history of the leaks that you can find in the websites we just talked about. But this is pretty much useless if there are not many passwords and they can be brute forced. Passwords have been designed to be easy to type and remember, so they don't have a lot of entropy. And it's very difficult to actually estimate the entropy of a password. It's almost always overestimated because humans are really bad random number generators. For example, if you ask a bunch of people to pick a number between 1 and 10, this is the distribution you get. Yeah, it's not really uniform. For some reason, people seem to like the number 7. It's not right in the middle. It's not too much on the left or the right. I don't know. This is weird. But my point is that humans are very predictable. Which is why modern password crackers don't try every single password blindly. They use permutations and Markov chains and neural networks to try what is going to be more likely first. Also, GPUs and ASICs are super fast, especially if they have to do the same thing on very large vectors, such as try many passwords at the same time. You can find a lot of passwords from previous leaks. They can be freely downloaded everywhere. And people like to reuse passwords. So if a password has been recovered, well, you can be sure that everybody's going to try this password on different websites, and it's going to have more than one match. So what about the remaining 30%? Well, same thing. You can compute hashes really quickly these days. So yeah, what can we do? Introducing what you can find, and there is something wrong in my slide. This is not in crypto hash, but in crypto.pw hash. So PBKDF2 is a very simple construction, which is going to recursively apply the same hash function many times, just to be slow. Why? Well, just to make a brute force attack against a password or anything with low entropy slower or more expensive. A more interesting function you can use, which is also not in crypto.hash, but crypto.pw hash, is called bcrypt. This is a cache hard function. It's going to require a lot of random memory accesses. So these are just reads, but a lot of them and in unpredictable locations, which is something GPUs don't like at all. If the whole lookup table fits in the L1 cache of a CPU, this is going to be super fast. If it doesn't fit, it's going to be instantly super slow. So a GPU is going to be usually way faster than a regular CPU for this. And ASICs can do a pretty good job, but it's going to be very expensive. So that's pretty nice. This is how to use this specific function. That's pretty simple. You get a password, which is Zig rocks, which is not a good password. And the second parameter is essentially a work factor. So this is going to be how many iterations this function is going to go through. And what you get is a string. And this string is just like text. It's like base 64 encoded. It's not exactly base 64, but it's just some text that you can directly store in a database. And if later you want to verify that Zig rocks is a correct password, you can compare what you previously stored with what has been recomputed for Zig rocks. So the API is very simple, just two functions, hash and verify. Okay, let's switch to crypto.sign. This is just a signature system. ED 25519 is a pretty common signature system. It's actually a really good one. If you use SSH, you probably use it every single day. So a signature system is something with a bunch of functions. You can generate a key pair, so a function that returns a private key and a public key. So instead of private key, I tend to say secret key, so that you get PK and SK instead of PK and PK. So once you get a key pair, if you know the secret key and a message, you can compute a signature for the message. And given a message, a signature, and a public key, you can verify that the message has been signed by someone who knows the secret key. So that can be very useful if you want to sign firmware updates or software updates or whatever. And ED 25519 is interesting because keys are really small and signatures are small as well. So you can even enter them directly on a command line if you want to. This is really great. How to use that in Zig? Pretty easily. You have a function to create a key pair, a function to sign, a function to verify. So this system is fast and secure unless you have some way to have a fault attack during the computation of a signature. It could be a raw hammer attack, it could be a voltage glitch, whatever. This is not so common, and usually you don't have to care about that. But if you do, as of today, a medication which is believed to be efficient is to add some noise, some random noise during the computation of a specific step of the signature. And Zig is one of the rare implementations that allows you to do it. And if you look at the previous slide, when we had the sign function, we had the message, we had the key pair, and the third parameter was set to null. But you can set this to a random, it's not even a key, just some random bytes, and it's going to add this extra protection for you. We also support batch verification. So if you have a lot of signatures you want to check very quickly, this is going to be faster than individual checks. This is great for blockchains. So ED 25519 in the original paper has been underspecified. For example, there are different ways to represent the same public key, or different signatures can be valid for the same message. And it's okay for what it was originally designed for. However, applications may have different expectations. So after the research, the original paper and the RFC were published, a bunch of research papers have been published, and implementations have been improving over the original specifications as well. And to date, Zig has the only implementation that achieves both maximum security and maximum features. That's pretty cool. So there's a bunch of things with 255.19 in their names, plus some related stuff. I'm not going to talk about them today for a very good reason. This is going to be addressed in a different talk where I will be talking about fast finite field arithmetic in Zig, elliptic curves, and everything you can see here. So let's not spoil it. And switch to crypto.knuckle. You might be familiar with knuckle and tweet knuckle, and you're supposed to say thought, not knuckle, whatever. So knuckle is, or actually tweet knuckle, because this is probably the most popular implementations with Ellipsodium right now. This is a very small library that was published as 100 tweets a couple years ago. And since then, people have been rewriting tweet knuckle in many, many different languages. In particular, in JavaScript, there is tweetKnuckle.js, which is used everywhere because it's very small, very easy to use, and it's a very simple way to have crypto that you can use pretty much everywhere. It's compatible between different languages. It's easy to embed on any application, so it's pretty nice. You can even find it in the Go standard library in crypto.knuckle.blah, blah, blah. And in Zig, we have everything that tweet knuckle has. So we have all the constructions from knuckle, including X salsa, which is something I talked about a couple slides before. But what's probably more interesting is the secret box, and seed box constructions. Remember that when you send a message, you need to send the ciphertext plus the tag, plus if the recipient doesn't know the public key, you need to send the public key. How do you send all these things? Well, whatever you want. You actually can use any serialization format you want, but these specific formats, secret box, bot, and seed box, do it for you in a pretty standard way. So let's take a look at seedbox, which is something you can find in Ellipsodium and Go. This is an extension to the original tweet-knuckle API, but it's probably what I would recommend. So this is very easy to use. You can create a key pair. So Joe has now a key pair. Joe KP is a structure with two members, public key and secret key. Now you want to send a message to Joe. That's very easy. You take your message and using Joe public key and the message and the function seedbox.seal, boom, you get a ciphertext. And that's it. Joe receives the ciphertext and he can decrypt it using the secret key. That's it. There's still one thing to pay attention to. When you encrypt something, in addition to the message, you need to reserve some space for extra data, such as the public key and the nonce, which is why you have the ciphertext whose length is the length of the message plus seal underscore length. You don't have to compute details for you. This is exposed as a constant. So very easy to use, and it does everything for you. Some takeaways while I've been working on crypto in Zig. First, result location semantics are great, especially when you have to chain multiple computations. That was very useful for all the elliptic curve arithmetic. Very clear, very nice to read and write. I love this. You know that you can write very readable code without paying some extra cost because of extra copies or whatever. A surprising thing is the inline keyword. If you just trust the compiler, you get pretty good performance. However, sometimes adding inline can completely change the performance of a specific function in a good or in a bad way. Sometimes you add inline and it's going to be twice as fast, which is pretty impressive because I was expecting the compiler to do the right thing, but sometimes it really, really helps. And sometimes it can be catastrophic. You add inline and everything becomes really, really slow. So how do you know when to inline and not to inline? Well, I don't know. Actually, to be honest, I've been just trying to inline a function, benchmarked. Oh, okay, no change. Okay, whatever. Let's try to inline something else. Oh, wow, it's faster now. Okay, let's try to inline something else. Oh, it's slower. Okay, so this is pretty much what I did until I found.
Oh no. It happened again.
Very readable and generic way.
Frank, sorry. We lost you again for
Yeah.
10 seconds. You were talking about
Oh,
inlining. Yeah.
okay.
I think occasionally you get like a more substantial loss of packets or something. I'm pinning this on you,
Okay,
on your connection, not mine, because I see that I am not dropping frames, but it doesn't matter anyway. Sorry. You were saying?
Okay, no, this is probably my provider, but okay. Am I back to it?
Yes,
Okay.
yes, you are, absolutely. If I can speak with you, then
Cool.
we are live.
Perfect. Okay, so yeah, so inline is definitely something worth trying. It can drastically improve performance or decrease performance. So the only way to know is to try, benchmark, retry, rebenchmark, and see if you can get a happy combination that provides optimal performance. Don't trust the compiler. It usually does a really good job at figuring out what has to be inline and what should not be inline. But sometimes an explicit inline keyword can really help. Also, vector instructions in Zig are really great. You can write some very simple code, which is going to be generic. It's going to work everywhere, so you don't have to use assembly or intrinsics. This is really nice. However, whereas so far in the implementation I vectorized on x86-64, it provides a great speed improvement. When I benchmarked the same code on ARM CPUs, it was actually slower than generic implementations. I don't know why at this point, and I haven't had the opportunity to try vectorized implementations on other CPUs as well. So what you have in the crypto right now has vectorized implementation just for Intel CPUs. For the rest, this is something I have to investigate. Zig is a great language for crypto. It has a lot of really nice features. One of the things I really liked is the fact that it does checked arithmetic, which was really useful to debug some of my code. That's really cool. But most importantly, the community is awesome. When I discovered Zig and I saw that it had some crypto, I submitted a very small pull request. I don't remember what that was. Just a tiny bug fix, whatever. And I got some really, really nice feedback, and my PR was merged right away. I was like, wow, that's cool. Let's try again. So I sent a different PR, fixing something else, I don't remember what. And same thing, I got a lot of very constructive feedback. And that was great because I was totally new to the language. So it was definitely useful. And PR was merged. So I was like, okay, so this is why I kept sending more PRs. And this is not just because of the language itself, but also because of the community, which is very, very, very nice. Special thanks to people who took some time to review my PR and help me. Terminator, Vexu, Firefox, Lemonboy, KubeCon, Rocknest, Dadaman, Andrew, of course. I probably forgot a lot of people. You're all awesome. So, of course, special thanks to you as well for watching this talk to the end. And thank you. Now, if you have questions, go ahead.
Awesome. Thank you very much, Frank. Give me a second to switch to the Q&A view. Okay, there we go. That was awesome. So thank you very much. Actually, let me give you also a particular thanks from my personal point of view, because not only you covered what you contributed to the standard library, but you also went through the effort of writing a proper introduction to how to use all these cryptography tools. So thank you very much. I've been trying to give myself talks, or in general trying to produce stuff also for maybe not necessarily newcomers, but people that are approaching a particular subject for the first time, and who might appreciate more a presentation that gives them a ramp up rather than just throwing at them the advanced stuff right away. So thank you very much again.
Yeah, no problem.
Okay, so while people start thinking about questions, by the way, if you want to ask a question to Frank, you can write it on Twitch chat. Discord is fine too. Same with IRC, in case you don't have nor want to have a Twitch account. Just remember maybe to tag me so I don't miss the notification. In the meantime, while people start typing, let me ask you, Frank, the usual ceremonial question of how did you discover Zig, and how long ago was that?
So I think that was on Hacker News. It was a blog post about Zig being a better compiler, better C compiler than C compilers. So I just tried it to compile C and nothing else. And I was like, okay, this is cool, nice project. I didn't try Zig as a language itself. But yeah, I was aware of it. And many months later, actually, I was just looking around at what was on my SSD, and I found this directory called Zig. And I was like, okay, before removing this directory, let's give it a try for real. Try this language. So I did, and I was like, wow, this is cool. I love this language. And I kept looking, and I saw that it had some crypto. I was like, okay, even better. So yeah, this is pretty much how I discovered Zig.
Awesome. So you mentioned that you were trying to, so you use Zig to compile C, which also brings me to, if I remember correctly, libsodium is implemented in C, right?
Correct, yeah. And some
So
assembly, yeah.
why did you decide to go with C and not C++?
Because I'm more familiar with C, because it compiled faster, because when I tried C++ and Boost, I got error messages that were quite long, to be honest. Like when you try to use templates, this is just terrible. So I was quite discouraged. And yeah, and I think that most of the crypto written in C has never been ported to C++. People tend to use C more. I don't know why. Yeah.
Mm-hmm. Okay, let's see if we have a couple. We have a couple of questions already. So the first one is, well, it's from Bim Bolt. So nice talk. So they're complimenting you, and then they ask, might remove some deprecated algorithms like MD5. So I guess they're asking you, why did you include deprecated algorithms, and if it wouldn't be a good choice to remove them.
Okay, so first I didn't add them. They were already here when I discovered Zig. And one of my first PRs was actually not to remove them, but to move them to a different namespace, legacy or something like that. And then I got a review from Andrew saying, hey, no, we absolutely need these algorithms. They are not legacy. They are used in real applications, which is actually the case. For example, for the dwarf debug format, you need, I don't remember which one, MD5 or SHA-1 or whatever. So yeah, for any new applications, they're not a good choice. You should avoid them. We have much, much, much better as today. But for existing applications, you may still need them. So they're still around and they will stay.
Right. So another question by GW1. How does the speed of these algorithms in Z compare to other languages?
So as of today, my priority was to have a stable and nice API. It wasn't specifically on speed. So everything has been designed to support multiple implementations. For example, if we want a vectorized implementation specifically for AVX2, AVX512, whatever, we can have that. So the priority was really the API. That being said, it's pretty nice so far. It's totally acceptable. If you look at specific primitives such as edges, the implementation we have is just as fast as the one in Ipsodium, which is very nice. If you take a look at all the 25519 arithmetic, it's pretty fast, almost on par with other implementations in C and Rust as well. So that's pretty nice. And for the rest, especially for all the heads and trim ciphers, it's not as fast as it could be, if only because right now blocks are encrypted one at a time. This is totally intentional. It was just to have some initial implementations, once again with a stable API. And then the plan is to extend what we have with the ability to process multiple blocks at a time. But for application, this is not going to change anything. Your application is going to be faster just by recompiling with a new Zig version. So there is a plan to go just as fast as other implementations. It's not done yet, but the plan is pretty clear. And really, even as of today, performance is not bad. If you want to have actual numbers, there is the benchmark.zig file, which is a very small application that's going to run a bunch of benchmark for everything we have in crypto. And you know how many signatures per second we can do and how many encryption we can do, and you get all the figures. And it's really pretty good so far.
Awesome. Yeah, I think that you touched upon a point that I guess multiple people are independently moving towards, and by that I mean, going back also to the question from GW1, I think we are all contributing to the standard library with that same approach of trying to understand the API, trying to structure a subsection of the standard library, even though maybe the API for some things that are more complicated might not be even final, but you try to start approaching the problem from a structural perspective, and then hope that over time people will hopefully maybe even independently contribute parts of the implementation over time. Like that's what is happening, for example, with the async await stuff, the event loop stuff.
Yeah, absolutely. This is exactly the same thing for crypto. Yeah.
Let's see, other questions from Joachim. How have you benchmarked the speed on ARM CPUs? On which type of machine, etc.? Was it ARM 32 or Arch 64?
So this is Arch 64. I have a pretty nice router, not right now because I'm not at home, but at home I have a router with a very nice Arch 64 CPU. And what's interesting about it is that even if it's my ISP's router, you can run virtual machines on it. So I have a bunch of Linux distros running on it, and I can run benchmarks. So it has all the crypto extensions. So this is where I run my benchmarks. And more recently, I got the DTK, which is the Apple ARM development kit. And I run some benchmarks on this new hardware as well.
Great, right, and it also makes total sense that you want that type of stuff to run fast on routers. Now that I think about it, now that you mentioned that type of machine.
Yeah.
Let's see, more questions. Any thoughts on quantum resistant crypto? I've heard Intel has been working on that recently.
Okay, so first, for all the symmetric primitives, hashing, encryption, you don't have to care much about quantum computers as long as the keys are large enough. If you use 256-bit keys, you're safe. You don't have to change anything. So we are ready for all the symmetric stuff. Nothing to change. This is cool. However, for asymmetric constructions, for key exchange and signatures, Right now, if we ever manage to build a large quantum computers, the security of all the schemes we use today and the schemes we have in Zig is completely broken. However, we don't know if it's going to happen. If it does, we don't really know when. And I feel like we still have plenty of time to figure out what specific algorithms we want to use. Right now, a bunch of competitions are running. One of them is organized by the NIST, and it's about standardizing the next generation of signature and key exchange system to be post-quantum resistant. The competition is not over yet, so we don't know what kind of functions we will probably use in the future. And even once the competition is over, since all the quantum resistant algorithms really depend on problems that are fairly new, that didn't receive much attention over the few years compared to traditional cryptography, we may still have to wait a little bit before we can safely use them. So if it ever becomes a priority, if tomorrow IBM or whatever releases a large quantum computer and all the crypto is completely broken, yeah, in Zig, we will probably pay attention to existing post-quantum algorithms and probably implement them. However, as of today, this is absolutely not a priority. Even for Leap Sodium, this is not a priority because this is not a practical problem. This is more of something so that researchers get some funding. So yeah, if you want to switch to post-quantum algorithms today, you have a price to pay for it. Like keys are going to be large, or signatures and are going to be large, or it's going to be very slow, and implementations are pretty big as well and complicated, and implementations are not that great today. So of course, we have algorithms, we have a problem that's not a really practical problem right now. So probably the best thing to do is to wait a little bit, just pay attention to what's going on. And when we feel like it's time to switch.
Thank you. Just curiosity from me. So do you know what if things have improved from the virtualization point of view? I remember a few years ago I was like everybody just buying, so basically renting virtual machines from the usual cloud providers, and I remember that most of them did not have extensions enabled on the CPUs. Do you know if this has improved?
I don't know actually, and this is something you configure in your hypervisor, and some cloud providers do a pretty bad job at it. Honestly, I don't know. I feel like if you use something like Amazon, you're probably safe. You're gonna have everything available. If you use some smaller provider, maybe not. Yeah.
I see. Here's another interesting question. This is from me, by the way, not from chat.
Go ahead.
Maybe this is a controversial topic. I don't know. I come from the specific angle of ignorance, and I remember reading something about. So you mentioned NIST, right? And correct me if I'm wrong, but I believe that NIST is this American agency, organization of some kind that basically is sanctions what is good crypto and what is bad crypto, right?
They standardize crypto and they also make recommendations. And yeah, if you want to be NIST conformant, you need to use specific algorithms. Yeah.
Mm-hmm. And I remember reading years ago people being somewhat skeptical of NIST. They were saying that basically NIST would only would have an interest in only saying that what good crypto is actually crypto for which they have a backdoor of some kind. Opinions on that?
Yeah, of course. Well, tinfoil hat. But still, yeah, the one thing that happened and that made a lot of people skeptical is that among the recommendations they give, there is a way to build a random number generator using elliptic curves. And these things turned out to be completely broken. So they were recommending a way to generate something very important. This is something you can use to generate secrets. And that thing was completely broken. So people became suspicious. Another thing is that I'm going to talk about it more when we will be talking about elliptic curves. But for some elliptic curves, you need to pick parameters. And for some of their curves, they chose parameters without any justification. They look cool, just use them. But why? How did you come with this set of parameters? We don't know. So maybe this is completely randomly generated and this is safe. Maybe not. We don't know at this point. So people might be a little bit suspicious. However, they also made a lot of really, really good contributions, if only by running competitions. If we have AES today, this is because of NIST. So yeah, if you trust NIST, this is great. If you don't trust them, alternatives do exist. Yeah, but if you have to be standard compliant, you have to trust NIST no matter what.
Right. Okay, that was great. So let me ask you just a couple of final questions, maybe a bit away from crypto, out of curiosity, also for the people watching. And then I think we can end it here, unless more questions pop up in the meantime. So when we had we had a short talk yesterday when we were testing out all the streaming equipment and software, and we were talking about how you got into crypto from but you are also, you describe yourself on Twitter as a photographer. Can you tell me, I guess, again, more or less what you told me yesterday about your path into crypto? I think that might be interesting for people.
Okay, so this is two very different things. So let's start with my path to crypto, because this is more on topic. So a while back, I was working on a DNS server, and I was specifically working on something called DNSSEC, which is a way to make DNS more secure, but it's actually terrible. So anyway, I realized that DNS by itself, even with DNSSEC, was not so secure. DNS is great. It's a nice protocol. It works, but it wasn't designed for security. So I was like, okay, what could I do to improve that? So I designed a protocol which is still used a lot today called DNSCrypt. You can check out dnscrypt.info if you don't know about it already. This is a way to encrypt and authenticate DNS. More recently, it can also anonymize your IP address. So this is something I was working on just for fun. I just wanted to solve a problem in DNS. But in order to do so, I had to use some crypto, and I didn't know much about crypto. So I've been looking around for what kind of libraries I could use. OpenSSL looked complicated. And I stumbled upon something called Knuckle by Daniel Bernstein. And I was like, okay, that looks great. That was really state-of-the-art crypto. It was really fast crypto at that time, and it was very nice library, except that it was not designed for application developers. The library itself was not a library. It was just a bunch of C code, and you had to write your application around it. The compilation system was just super complicated. It would only run on the machine it was compiled on. So I looked at it and I was like, all right, I need to improve the code, not the crypto. The crypto, I trust Bernstein for having done something safe, but the code. And once you try to understand the code, you need to understand the crypto behind it. So this is what I started to do. And then I took some online class on crypto, and I got more and more interested in crypto. So I started to read papers, attend conferences, and be more and more involved in the crypto industry. And I started to release more crypto-related code, such as implementations of interesting papers. And yeah, so DNSCrypt became a thing, but besides DNSCrypt, I kept working on crypto, releasing new things and improving Lipsodium. As of today, Lipsodium doesn't have a lot of the original code from Knuckle. I rewrote pretty much everything and extended it into multiple things. Rewrote a lot of things in different languages, but this is not just about implementation. This is more about the field itself, which is constantly evolving. You were mentioning quantum computers. This is an interesting topic because people got interested into new problems to build crypto on. So this is also what keeps me interested in crypto today. It's the fact that it's constantly changing. So I keep reading papers, talking to people, going to events, and yeah. So this is how I went into crypto. And yeah, your second point, yes, I'm a fashion photographer. You can check out my website. This is prettysimple.images.com, all attached, or my Instagram, pretty_simple_images. This is completely different from my crypto work, but yeah, I'm a professional fashion photographer. You can find me during the Paris Fashion Week and London Fashion Week a lot. I do editorials, I do catalogs, and all these things. So it has nothing to do with crypto, but it's nice to do both.
Yeah, awesome. So I guess we can end maybe with one final question. If you had to give advice to people about photography, one piece of advice, what would you say?
First, don't waste too much money on the gear itself. Just go in a room, walk around, and trying to find the spot where you see the best light. And this is a really good start. You need to pay attention to the light more than you need to spend money on the gear.
Awesome. I think that's really good advice. Coming from somebody that probably spent way too much money on video gear for the people watching. Anyway, thank you very much. Is there anything else before we move forward?
I think we're good. Just enjoy the release party. And you can try Zig 0.7.0 right now because it's an exciting release. A lot of stuff happened since the previous one. So do it and enjoy. And Zig is awesome.
Awesome. Thank you very much. Thank you. Bye, Frank.
Thank you.
Okay, so we are now moving into the 10-minute break. Feel free to tap away, but after 2 minutes, come back because we're going to talk about Zig built-ins. So, yep, see you soon. Hey, it's almost time. 40 seconds. Oh no. Yeah, you try to send the blue screens, but they're disabled. Let me refund you the points. Though maybe I should really keep them. I don't know. I'll give them back. Okay, so we're getting close. Time to tap back into Twitch. Enough watching, I don't know who's playing now. Stop watching Shroud or something. There we go. Hello. Hello, hello. Okay, so I wanted a blue screen of that in the break. Sorry. Yeah, yeah, you got a refund. I haven't enabled them in that scene. I need to spend some time and maybe rethink these things and maybe add some and all in due time. So in other words, not today. Okay, let's take a look at this new talk. So I think the talk from Frank was awesome, very interesting. Thankfully, he covered another part of the standard library that I didn't have to cover. Of course, I would be able to cover it very easily. There's no discussion. I mean, my favorite number, my favorite random number is not 7, like everybody's. What a stupid choice. It's 1, of course, best random number ever. And I also use MD5 and salts in my MySQL database when storing passwords and credit card numbers and stuff. So NIST has nothing on me. But that said, I'm happy he did the work and I didn't have to. So I can focus on built-ins. So let's take a look at built-ins. So last time, we were looking at the standard library documentation, and I mentioned that the standard library documentation is not the language reference, and we went down the right path. We went down the standard library documentation. But today, like a game book that you read again and make different choices in, today we go down the language reference path and we take a look at what's in there. So nice slide that I was able to reuse. And another nice slide that I'm able to reuse is this one that tells you where to find the language reference. So you click download the documentation, and for each version of Zig, there's the documentation link that brings you to the language reference. And that's also what it looks like. And so today we're going to see what the built-ins are, what built-ins are in general, and we're going to see the specific built-ins that Zig has. Not all of them, not one by one, but we're going to take a look at them in groups. So first of all, what's a built-in? Why are they special? Yeah. So built-ins are a piece of functionality that is hard-coded in a compiler. Unlike the standard library, where the standard library is just a bunch of functions and scripts written in Zig itself, built-ins, I guess with the self-hosted compiler, built-ins will be themselves written in Zig, I guess. But they are not normal Zig functions. They are special, and they have a different role in when code gets parsed, analyzed, and then translated to machine code. So they are not normal functions. They are all prefixed with the @ symbol in Zig, so you can easily recognize them from normal functions. And as I said, they look like functions, but they're not really, or they don't always behave exactly as functions. So I'll tell you more on that later. But it's not, how can I say, it's not something, this last point is not something that you absolutely have to keep in mind every time you use them. But occasionally, you will, I have an example at the end of the presentation where you will see where understanding this concept might play a role. So as I said, what are we going to do today? We're going to take a look at built-ins by groups. We are not going too deep with the metaprogramming built-ins, even though they are probably some of the most interesting built-ins that Zig has. And the reason for that is that they clearly deserve a special presentation just for them, just about how to do metaprogramming in Zig, right? So we're gonna take a look at them. I'm gonna explain to you how they work, but the point is, at the end of the presentation, you might not feel confident enough on how they should be used. And so they're just gonna be some built-ins that we'll see among others. Also, built-ins are not set in stone, so you can expect them to change before we hit version 1.0. So there might be new ones that pop up, some that get retired. So even though they are not just part of the standard library, they are still something that is potentially subject to change. So Zig has 102 built-ins as of today. As I said, we're going to look at them in groups, not one by one. So let's start with the easy ones. And as we move forward, we'll see progressively more interesting ones. By the way, the grouping is arbitrary by me. You might disagree on how I did the grouping. You might disagree on whether one particular built-in should be in one group or another. I might have made a mistake, so don't take this grouping as something more than just me trying to organize them logically for the purpose of this presentation. So we have a bunch for math, and I think these are probably the most boring ones because it's math stuff, right? Division, multiplication, addition, sin, cos, exponential, log, etc. There are a couple that are colored, they are orange, because those are colored differently as a reminder for me to go and check how they look like in the source code. So let's go do that. Oh, sorry, not in the source code, I mean in the documentation. We have the documentation this time. So here's my friend Chrome, download the documentation. There's the whole documentation. You scroll down on the left and where the index is, and there we go, we have built-in functions. So again, I'm not going over all of them, but the two ones that I wanted to go over, which I think are mildly interesting, are mod and rem. So let's take a look at mod. Mod does modulus division, and if you know how modulus is defined normally, we basically, if you do modulus and something is negative, it always produces positive stuff. So the modulus between -5 and 3 is 1. While rem is kind of the same thing, but it gives you negative values also. So sometimes when you're doing arithmetic, you want one, sometimes you want the other, and Zig gives you both. So maybe this is a difference that is relevant to you. So again, math, boring. Maybe another thing that I should mention is that you can see that there are a bunch of div exact, div floor, div trunc. You will find especially two main different versions of the same function. One is exact and the other is with overflow. The idea is that in one, you assume that one of the preconditions for using it is that there is not going to be overflow. So you know it's not going to overflow. While the other one assumes that overflow might happen and it will report it correctly. As you can expect, as you can imagine, the reason why there are two versions is because the one that doesn't have to check for overflow is faster. But if there is overflow, that's undefined behavior, which means that in release safe and in debug mode, you'll get a panic. In release fast mode, you should not have done that, and I don't know what will happen because it's undefined behavior. So again, not super interesting. So let's move forward. So we have covered 22 of them. So why are these math functions built-ins? Why are they not just defined in the standard library? And the answer is because these tend to map to hardware instructions. So if you are writing code where it's important to know if an operation is supported by the CPU or not, etc., these tend to give you that property. So you will read in the documentation that they say that they always work, even if there is no native instruction in the CPU. But when that type of instruction is available, then the built-in will use that implementation. You should take a look at what their equivalents in std.math for better error handling. Again, if you use, for example, one of the with overflow ones, you will get reported that an overflow happened. But the interface is more low level than what you get from std.math. So unless you're writing something that is extremely performance sensitive, just use std.math. That's the right choice. Also, some of these operations, they accept different types of arguments, and they also work on vector types, which is nice. And if you were here for the previous talk by Frank, I guess cryptography is one of those situations where you might care about this type of stuff, about vectors, about having your operations tend to map nicely to what the architecture provides. But again, this applies mostly to math, and as we will see soon, also to bit fiddling. But not all built-ins are about hardware instructions. There are some other built-ins that are much, much more high level. So we'll get to that too. So next category, as I mentioned, bit fiddling. Very quickly, swapping bytes around, reversing bits, count the number of leading zeros, count the number of trailing zeros, CLZ, CTZ, count the number of bits set to 1, shift left, shift right. Again, nothing super interesting here. Useful, yeah, but not super interesting. So we are at 30 over 102. Now I think we're going to start to get into more interesting stuff. So atomics and memory stuff. I'm not going to get into atomics and memory barriers and stuff much because, of course, it's another one of those topics that I could probably cover in the blink of an eye perfectly. But I think I'll wait for somebody, I don't know, like King, wink, wink, like Proti, to give a talk on the subject. But let's take a brief look at some of them. So let's take a look at atomic RMW. So let me switch view. There we go. So atomic RMW. So this family of atomic this, atomic that, atomic that other thing, these are what are used to, well, implement atomic reads and writes to values, right? Which is one of the primitives used for locks and concurrency stuff. If you watch the last presentation by King, so by Proti, I think he mentioned these operations, but he also mentioned some problems with these specific operations and how sometimes they might seem the most optimal thing that you can do, but there are, like, memory is complicated and there is a price for using some of them, a price that you might not be aware of and not really be willing to pay, really, if you knew. So these alongside, let's take a look also at fence. Like fence, I think it is also interesting. So fence function is used to introduce happens before edges between operations. Again, I don't know much about this stuff. Like previously I was clearly joking, right? I don't know much about this stuff, but what this looks like to me, fence, I guess it's kind of like fsync, but for memory. Again, referring to the presentation by King from last time, he mentioned how he gave a few examples of how memory and CPU registers and local memory on the cache on the CPU, how they have to coordinate and interoperate with one another. And basically, I guess memory kinda is structured to some degree the same way that we structure file I/O, where not everything gets flushed down to the hardware immediately, but there is some batching that can happen, and maybe sometimes you don't want that, and that's when you have fence and fsync and stuff like that. Again, I don't know, just general statements on why this type of stuff is useful. There's also compare exchange, compare exchange that, but again, this stuff definitely deserves a special presentation on its own. So next thing that we wanted to take a look at was memcopy. So memcopy is, well, let's take a look at the definition. So this function copies bytes from one region of memory to another. You must ensure that the two pointers don't overlap. And this function is a low-level intrinsic with no safety mechanisms. Most code should not use this function. Instead, use something like a normal for loop where you vary bytes from one place to another, because the optimizer is intelligent enough to turn the above snippet into a memcopy. So it's available for you, but you probably should not use it and just stick with a normal for loop. And on top of that, there's also standard library implementation of this too. So again, with memory stuff, you can imagine that we are still in the realm of things that have a fairly deep connection with what the architecture offers. So we still have the same situation like with math, where you have the low-level implementation as a built-in, and then the nicer interface that's the one that you should use in the standard library. Next we have WASM memory size, WASM memory grow, and shuffle. Oh, and that's interesting, right? We have a couple of functions about WASM. So let's take a look. WASM. So WASM memory size. This function returns the size of the WASM memory identified by index as an unsigned value in units of WASM pages, which apparently are 64 kilobytes in size each. So we have a couple of intrinsics that are about memory, but these are about one very peculiar architecture, right? A virtual one, not even a physical one. That's WebAssembly. So we have these, we have WASM memory grow. Again, both also, if you read the documentation, it says that they're not really for people to use normally, but they are like low-level things to build memory allocators upon. But I think it's interesting that we have built-ins in the compiler specifically dedicated to WebAssembly. The final one was shuffle. So let's take a look at shuffle. Shuffle, I think it's another interesting one. It's about vectors, and what it does is you have a mask that tells you, so a bit mask that tells you whether to grab items from vector A or from vector B. And it's kind of a, I don't know, I was about to say a XOR, but probably that's not the best definition, but you get the idea, right? So either you pick from the left or you pick from the right, and this produces a new vector. And I'm guessing that this is here because also it's implemented in a bunch of CPU intrinsics that can do this faster than you would be able to with normal code. So I think that was another interesting built-in to take a look at. And with this, I think we have all the atomics and memory stuff covered. Splat is another similar one to shuffle. Next category, casts and conversions. So these are the ones, 17 of those. The difference, let's see, should I take a look at some first or talk about casts and conversions? Well, let's take a look at, actually, no. Let me first mention why I put both words in the title. So a cast, generally speaking, is taking one value that is that either in the compiler has a type, but you want another type, but you know that the value is precisely what it's supposed to be. It's just that the type is not properly expressed in the code because maybe you're doing something unsafe. Like if you think about in C, since you don't have generics, oftentimes you move around void pointers, but you might know what's behind that void pointer. You might know what the actual type is. So you cast that void pointer to a pointer of the right type, and you pray that you got that right. While conversions are about changing from one type to another type. So a cast just changes the type signature of a bunch of bits, while conversions reinterprets those bits and changes them to produce a new value. So for example, float to int is not taking the bits verbatim and saying now this is a integer, because you would get a weird integer, right, out of a float representation. Float to int takes the bits, interprets what the float number is, removes whatever is after the comma, and transforms that into a normal int. But for example, bitcast, it takes whatever type you have. Actually, let's take a look at the documentation, right? So let's go to that. Let's start with bitcast. So bitcast, bitcast converts a value of one type to another type, and it can be used for these things. For example, convert from F to U. Works at compile time if value is not a compile time. It's a compile error to bitcast a struct to a scalar type of the same size, since structs have undefined layout. However, if the struct is packed, then it works. So you can make a lot of weird things, weird changes. Let's take a look also at pointer cast. Pointer cast. Converts a pointer to one type from one type to another type. So you have for example, a pointer. We talked about pointers last time, right? So maybe you want to cast a pointer to a unspecified number of elements to a just a pointer of only one element. There are some, or vice versa. Yeah, sorry, vice versa works best. So these are casts that allow you to undo unsafe things. So these are casts where you need to get this stuff right. But this is not the same as is the, I guess, what you should prefer to all others, unless again you are doing something that more specific. And as only does safe casts. So I guess type coercion. So it's coercions are the safe subset of casts. Let's take a look maybe also at, we were looking also at align cast. So this is interesting. Align cast, if you don't know anything about memory alignment, then this is something that might trip you occasionally. So if you're trying to do weird things, like it's a struct, but I'm trying to think about it as an array of bytes, or vice versa, I have an array of bytes and I want to cast that to a struct because I know that this thing is actually a struct. Why is the casting not working? And sometimes you get these message from Zig that tells you, well, the alignment is not the same of these two things, and so what you're doing doesn't work. So what is this alignment thing? I can't give you a full explanation here because again, this is another of those topics that really deserves its own presentation in my opinion. But long story short, certain types of things in programming have to have a particular alignment in memory for them to work correctly in their corresponding architecture. So, for example, actually, let me start again. Let's say you have a, I don't know, 32-bit CPU. 30-bit CPUs, I don't know, the normal ones, the ones that people normally use have in the computers, so x86. They want to have certain things aligned to the word boundary. So you know that a 32-bit CPU has a 32-bit long word. So each instruction is 32-bit long. And that's how the CPU digests your code. And when you ask, for example, memory from an allocator, the allocator maybe gives you memory aligned to the word, maybe it doesn't. C allocators normally do because you don't have a good way of talking about alignment in C, but a Zig allocator might have an allocating strategy where it can give you memory that is not word aligned, for example. So that type of memory, if alignment wasn't specified in type, you would move around memory of a certain type, you would move around memory that maybe you want to use to store a certain type, but then operations on that type, normal operations, don't work if that chunk of memory is not aligned to the word. So long story short, if you end up with problems with alignment, you might want to take a look at also align cast and align off, which is not listed here because align off is not a casting operation, it's an introspection operator. It tells you the alignment of a specific type. And also when allocating memory, you can use this information to request a particular alignment from the allocator. So again, this is stuff that requires its own presentation for a proper explanation of why things are that way. I just wanted to briefly mention just problems that people might encounter normally. Okay, let's move forward. Cast and conversions. Yes, as I was saying, prefer as over other options, unless you know what you're doing. That's a reference, by the way. Check the safety properties of a cast when using it. Some casts are inherently very unsafe because you are asking Zig to convert from one type to another, and there is no way for Zig to assert that what you're doing makes sense. Some other casts are instead more safety checked. So, for example, we were looking at a line cast, right? A line cast, a pointer alignment safety check is added to the generated code to make sure that the pointer is aligned as promised. This is something that has to happen because, again, the alignment of a chunk of memory that an allocator returns to you is a decision that the allocator makes at runtime, but at least it's something that Zig can check. So when you ask for a specific alignment, Zig will check that actually that pointer is really aligned to that number of bytes and otherwise panic. So be aware of what the safety properties are of these type of things. Some are checked, some in debug and safe mode, some others really cannot. Also, casts work best when you combine them with introspection built-ins that we're going to see later. And also because when you are doing introspection, that's when you can catch errors and handle them yourself. If you do a line cast that fails, that will produce a panic, and there is no way of recovering from a panic. But if you first inspect the alignment of something using a line of and then reason about it, then maybe you can find alternative solutions in your code if it's something that makes sense in your application. It's not always possible. Alignment especially can be annoying, but you can work around some of these things, for example, by padding stuff yourself. Again, this is advanced stuff. If you're doing this stuff, you know what you're doing. But again, keep in mind that they work well together. Normal programming. Yep, there's also those. These are actually most of them are actually the ones that everybody knows. And so there's a few that start with C, and these are for importing C code into Zig. So C import, I think it's the main one, and in C import takes a block in which you can include, define macros, undefined macros. So there are some header files that expect you to define some symbols, and then you can combine everything together to import stuff from C correctly. More interesting are compile log, compile error, and embed file. So let's take a look at those, and then we can move to the second column. So compile log and compile error. These are probably my two favorite built-ins, maybe after import, since I like using other people's code. So compile error and compile log basically write a message. They're like a print message at compile time. A print message, but they print at compile time, and they're useful for reporting errors and I guess sometimes also debugging things that happen at compile time. So the difference between compile log and compile error, they kind of do the same thing, but compile log, when you hit a compile log, you don't immediately stop the compilation. Compilation proceeds until the end, and then all the compile logs get printed out. While compile error, the moment you hit one compile error, then compilation stops immediately. So let's take a look at what the documentation says for compile log. So this function prints the arguments passed to it at compile time. To prevent accidentally leaving log statements in a codebase, a compilation error is added to the build, pointing to the compile log statement. This error prevents code from being generated, but does not otherwise interfere with analysis. The function can be used to do print debugging of compile time executing code. So compile log basically is something that, for example, let's say that you have something that is very complicated and you want to check what's going on with compile statements. You could even leave them behind a flag, behind a if statement that gets resolved at compile time, of course, for example, or just put a couple of those to check what's going on and then delete them afterwards. But Zig has no warning system. So when I say that Zig has no warning system, it means that Zig doesn't like to leave messages that print randomly from my compilation. That's why for the compilation to succeed, these cannot be part of the compilation result. One use that I think is very good for compile error is if you have something that requires people to pass in a type. So for example, you have to use any type and you want to, then you have to check that the type that you're given is correct. Compile error is a good way of explaining to the user what they did wrong. So, for example, if they're supposed to pass you a number and they are passing you something that is not a number, you can tell them, you can write in the compile error message where after you, in the if statement where you're checking that the type that you were giving is a numeric type, you can also say, you were supposed to pass here a numeric type. So these compile errors can help you enforce constraints, and I think they are part. They can be messages that are nice for people to see that become part of your API design. The last one that I wanted to see of this con was embed file. Let's take a look at embed file. Embed file. Oh yes, embed file is really nice. So embed file, it's a function. This function returns a compile time constant pointer to null terminated fixed size array with length equal to the byte count of the file given by path. The contents of the array are the contents of the file. So this is a very long-winded way of saying that you can use a embed file to read files into your Zig code at compile time. And that's really nice because then you can, at compile time, transform a file into a string into your program. So you can bundle stuff into your program, which can be useful sometimes because maybe it would be annoying to have a second file that you have to put in the same folder and read into memory every time, while you could just embed it into the executable, and that's nicer. And also, it allows you to reason at compile time about what's written inside. So you could read the file at compile time and then reason about it and produce some types based on what's written in the embed file. So if you think about protocols like gRPC or I don't know, Captain Proto or whatever, all these formats, or even you could even get a what's called JSON spec, I think. So you could get any of those specification formats that tell you how a type should be structured and actually make that become a real type. There might be some limitations to that approach today based on the fact that metaprogramming doesn't allow you to do everything yet, but it's an open issue, so we might very well get this functionality in the future. And still, there are some very interesting things that you can do, I think, with this. So I think that's a very nice primitive to have. So the other column had, well, import. Import, I think, doesn't need any introduction. I guess we all know import. But then there's also, well, export, which is for exporting symbols to C, for example. But I think the more interesting ones are set, align stack call, deval branch quota, float mode, and runtime safety. So let's take a very brief look at those. And again, as usual, I don't know everything about those, so I'll give you a couple of comments based on what I know best and other, I guess, like just reasonable guesses that I can make by looking at the name. So set align stack says ensures that the function will have a stack alignment of at least alignment bytes. So one thing that this documentation is not saying that is then, but that it is said for other built-ins of this type, is that these built-ins they set something in the compiler, they change some setting in the compiler for the scope that they are in. Well, I guess set align stack is for the function scope that they are in. So the idea is that you put them at the beginning of your function to add some hints to the compiler about what should happen. So set align stack is about stack alignment for the function. I have no idea when this would be useful. My guess is maybe for particular architectures or for particular calling conventions, maybe, I don't know. Set called, this I think is easier to understand, tells the optimizer that a function is rarely called. So how does this work? Again, I have no idea how this works precisely, but my uneducated guess is that function calls compete for space on the registers, which is the preferred part of memory rather than the stack, right, to put arguments, for example, and stuff. And by saying that a particular function is not called very often, makes the optimizer strategize better about where to put each arguments when a function body has an if branch, and then inside that if branch you can call function A or function B. If you know the function A is rarely called, you will basically prioritize function B for the better spots where to put arguments, and function A will get all the lower stuff. So that's why it ends up being in better performance. Again, just a guess. Maybe different architectures can do different type of reasonings based on set called. Set eval branch quota, that's for the comp time stuff. So comp time is never going to loop forever. Comp time loops up to a point in terms of looping inside while loops and recursive calls. But then after a while, it will fail, saying that compilation couldn't be done in a given amount of resources, which is this eval quota. That basically it ensures that your build is not gonna be stuck there forever. But so how long is what is the right amount of work that you can expect compilation to do? Well, it depends on your program, right? Simple programs are probably fine with the default quota, which is, I guess, 1000. But bigger programs that do a lot of stuff at comp time, that do a lot of reasonings at comp time, might be willing to wait more for that to complete. So that's where you can change the branch quota for a particular section of your code. Again, this is something that becomes relevant if you're doing a lot of comp time stuff. Set float mode. That's another interesting one. I don't know when it's used precisely, but apparently this is about float pointing arithmetic. There are two ways. One that makes float arithmetic follow IEEE compliance. So I'm guessing this is what you want if you're doing like float math on a client and on a server, and you want them to always converge to the same exact final solution. But if you don't care about this stuff and you're fine with losing some precision, then you can set optimize, which I'm guessing runs faster. There's a list of things that become allowed or other preconditions that the setting assumes. And apparently this is also something that you have in GCC when you set fast math. Floating point mode is inherited by child scopes and can be overridden in any scope. You can set the floating point mode in a struct or module scope by using a comp time block. There you go. So I guess this is also useful. Is this something that works on x86 64? Maybe yes, I guess. If GCC has a flag for it, I don't know, honestly. Maybe something only good for consoles. No idea. But that's what it does. Oh, and finally, that's the most interesting one, I think, set runtime safety. Set runtime safety allows you to set, if you want, like you're compiling in release fast mode, but there is a bunch of code that you want to still keep safety on, you do set runtime safety true, and you re-enable runtime safety for this chunk of code. And then you can you can do the inverse. Maybe you're doing a release save, but it's a particular code path that you want to be as fast as possible. You know it's correct. There are no situations where, I don't know, like untrusted input can influence what's happening in there. And then you can set runtime safety false for that specific branch of code and just enjoy the full performance. So we know that we have all the release modes that Zig uses that allow you to switch from one configuration to the other, but we have also greater granularity than this, right? You can override this setting also on a per scope basis, which is pretty nice. So we've done also the programming ones, and we are up to 73 out of 102. So we are nearing the end. Runtime and async magic. Again, this is an arbitrary way of bundling these built-ins together. Maybe this is not the best category, but runtime alone had too little things, so I just decided to merge the two. So runtime and async magic, and I think there are maybe some. Oh, I should have moved, I think, also call in here. Maybe. I don't know. Anyway, sorry. So runtime magic. So the two columns in this case, this is runtime magic and this is async magic. So runtime magic, breakpoint, and panic. They're all colored because I think they're all interesting. So let's take a look at all of them. So breakpoint and panic are really nice. And I think you've seen me use them in the advanced Hello World talk. So breakpoint here, it's a function that introduces a platform-specific debug trap instruction, which causes debuggers to break here. So it basically puts in the middle of your function some invalid code, some invalid machine code that is, or I don't know, I guess it depends on the platform, whether it's normal invalid code or something different. But anyway, it puts in there a special instruction that is useful for breakpoints. So normally you open a debugger and then inside the debugger you can say in which line you want to break, but sometimes, I don't know, this doesn't work super well, or it's just easier to write a breakpoint in there, compile, just make it run and have the breakpoint trigger automatically. What also this allows you to do is sometimes you want to breakpoint only when certain conditions happen, and that might be problematic with your debugger. And so this allows you to basically put the breakpoint instruction inside a if block where you check for all the conditions that you want, that you expect to have happened, become true. So I think it's a very useful built-in. The other one is panic. I used to know how the alphabet ordering guys were. Panic. So panic calls the panic handler function, which is, well, you have a default one, or you can re-implement it. Again, this is something that we went over in the Advanced Hello World talk. But yeah, let's read the documentation. So invokes the panic handler function. By default, the panic handler function calls the panic function exposed in the root source file. But if you haven't specified one, then there's one inside std built-in default panic inside the standard library. In general, it's better to use the panic function inside debug. However, panic can be useful in two scenarios. One is from library code, because calling the programmer's panic function if they expose one, because that way you will call the programmer's panic function if they expose one in the root source file. And also when mixing C and Z code, because calling the canonical panic implementation allows you to call the canonical panic implementation across multiple object files. So that panic is another useful one, but again, I think it's nothing surprising there. Then we have the async stuff. Again, the async stuff, it's another example of things that kinda require their own talk. But async is, I've been thinking about doing a talk on async stuff. It's challenging. It's still a work in progress in Zig, also in many ways. Like the API is not finalized, and I think there's an accepted proposal for a new operator select, which we don't have yet. So that's another reason why waiting for that to happen before doing a async talk might be a good idea, because otherwise your talk becomes very quickly incomplete and or obsolete. And it's a lot of work to explain async, man. But we'll get there. I swear I'll do that one day. So we are looking at async call. So async call is not only, so async stuff is, as I just said, is not super easy, but async call is an extra layer of complexity to explain. So basically, async call is something that you should not use almost ever when you're doing async stuff. And what it does is, well, it performs a function call, right? So you pass it a function pointer, you pass it arguments as a tuple, and then it gives you, and then it calls the function. So it's not here, it's in another section, but there's also normal at call, which just performs a function call. But you know, when sometimes you have your arguments, you have them in some kind of list, right? Which might be a Zig tuple. So you have your arguments in a list, and then you have your function, and you want to call that function with those arguments. And normally you would just call, function, open parentheses, arguments, but you have them in a list. So you need this little bit of metaprogramming that allows you to say, please do a function call with this list of arguments. And that's what call gives you. Async call, more in particular, does async function calls, which have their own peculiar calling convention, and they have also their own peculiar system of writing the result to a pointer that you can give. And to explain why this is like this, it's complicated. So long story short, it's a way of doing async calls, allowing you to do an async call when the arguments that you're given, that you have, are in some kind of list, and at the same time the function pointer is like the function that you want to call in async mode is a function pointer. So it's not just a function that somebody has passed you as a function type, but it's a runtime function pointer, which is even more problematic. So long story short, it's for async stuff that you should try not to do too much of either also. Next one was frame and frame. We have two frames, frame, lowercase frame, and frame, uppercase frame. Built-ins that start with the uppercase value are, with the uppercase, initial letter, are about types. So tag type gives you a type. Frame with an uppercase F gives you a type. This gives you a type. Type gives a type. Type info doesn't give you a type. It gives you an instance of a particular struct type that is defined somewhere. So the first letter being uppercase has a meaning in that sense, because in Zig, types are Pascal case, right? It's Pascal, I think, having the uppercase letter. Oh, and Alex is also. Oh yeah, Alex is pointing out the two interesting irregularities: import and C import. Right, that's a good point. But anyway, even more fringe. So let's talk about frame and frame. Let's do uppercase frame first. So uppercase frame, it returns the frame type of a function, and this works for async functions as well, and with any function without a specific calling conventions. So at frame gives you a type that represents your current function frame. For normal functions, I guess it's good that it works, but it's not as interesting, I guess, as async functions. With async functions, it's very important to be able to refer to the async function frame, which to say in a very quick and dirty way, to give a very quick and dirty explanation, async functions, well, every function requires a memory to run, right? Normal functions, functions that have a normal calling convention, like the default one in Zig or like even the C one, what they do is that you to run a function, you need, I don't know, 10 bytes of memory, because there's a couple of small variables and nothing much else that store state, do something with the state, and then return a result. You need 10 bytes. What happens is that you have the stack that has a limit telling how much of that stack is being actively used by other functions. You bump up that by 10 bytes, and then you can use that space to run that function. Async functions kind of have the same necessity, but by nature of how they are async, you tend to want to be more how can I say? You tend to want to be more creative with what type of memory you want to use to run them. So it's more probable that you want to use heap memory, for example, to run an async function than stack memory. Well, it's not, I would say, sorry, it's not more probable proportionally, but it's more probably that you want to do that with an async function rather than with a normal function. So async functions, you end up using frame very often, because you end up saying, well, I want to run this async function on the heap, because the async function is supposed to continue running, is supposed to live more than the current function that is instantiating it. Because if you were to use stack memory, the moment the current function returns, that memory is not usable anymore, right? And you end up with all kinds of undefined behavior. So long story short, it's not uncommon to think explicitly about the memory that an async function needs to run, and @frame gives you the relevant type, so you can pair that with a memory allocator, so that you can heap allocate the memory, and have your async function live for longer. You don't do that in higher level languages because everything tends to just get chucked on the heap anyway by the compiler. So like if you're thinking about Go has the same requirement, but in Go, you don't do any of this stuff. You just do Go whatever, and then Go decides where the memory should go. And sometimes it's the right decision, sometimes not really. I think if you've read a few like blog posts about I think who was recently that had problems with this. I think, well, I come from the database world, so I've been reading a bunch of database stuff, and I think CockroachDB is written in Go, or it was written in Go. I might be wrong with this. I might be misremembering the database in question. But anyway, there were these database people that were using Go, and they were annoyed because occasionally they wanted something to be on the stack and not escape on the heap, but the Go compiler didn't know how to do that, and that's the beauty and the curse that you get from garbage collection and languages that do automatic memory management. So frame gives you the type, but then sometimes you want to refer to a pointer to your own frame that you're living in. So if when a async function is running, for example, it's not uncommon for the function to say, well, I want to suspend. Async is about all this whole juggling system where a function can suspend and then be resumed at a later point by another function running maybe on another thread. So what happens often is that the async function does a bunch of work, then it has to wait for one reason or another. So what it wants to do is register itself to a system that will be able to resume it later and then suspend. And that's when you need a pointer to the chunk of memory that you are running over, that you are running on. And that's what lowercase frame gives you. And in fact, lowercase frame gives you a pointer to the frame of the current async function running. And there is a lot to say about async function, frames of async functions, the types of async functions, async function frames. So the types that these frames are and their pointers are. But that's a story for another talk. So what else was in there about async functions? Oh, there was also frame size. The frame size is the equivalent of doing size of frame func, because that's, I guess, another thing that you tend to do often, especially with async call. Because async call, you can see that the frame buffer is a slice of memory. It's not even properly typed, as you can see. Anyway, that's definitely a story for another day. Async stuff is complicated. Let's move forward. Introspection. So introspection gives you information about stuff, and there's other stuff that I think qualifies probably as introspection, but they put it in the metaprogramming section, which is the next one. But anyway, again, a lot of stuff that either we mentioned or that you can, or that you already know from other languages, maybe. So align of, we were talking about alignment earlier. This allows you to inspect what the alignment of something is. Bit offset of, bit size of, byte offset of, these are all offsets and bit sizes. Error name, I think it's interesting. So let's take a look at error name. Error name, this function returns the string representation of an error, which is awesome. So you know how errors are nice in Zig and have a name. It's not just a bunch of numbers that you move around, and maybe you have a header file that macro defines their names and maps them to numbers. In Zig, the names are more integral to they're part of the essence of what an error is. But sometimes you want to print their name, and so sometimes you want to be able to add them to a string or something, and error name allows you to get a string representation of a particular error, which might be useful for, I don't know, something that you want to do. Also, look at this. This function returns the string representation of an error, And if there are no calls to error name in an entire application, or all calls have a time known value for error, then no error name table will be generated. So if you're doing runtime error naming, then we might need a error table. Otherwise, everything can be inlined, I guess. If you only have a couple of places where you're just grabbing the error name of one specific error that is known at compile time, then we just need to intern that one string. We don't need a full table for them. Otherwise, if there are no mentions at all of error name, then we don't care about error names anymore. And that makes the executable even smaller. So that's cool. Let's go back to the other things that we're looking at. Oh yes, field parent pointer, size of, and src source. Let's start with size of. So size of is our good friend from C, right? That's what you do in C all the time. Size of this, size of that, to know how many bytes to allocate. In Zig, you don't do that much because you have a bit of metaprogramming, right? That allows you to talk in types rather than in bytes. But sometimes you want to do some math with offsets and stuff, and you want to know how much space a particular type is occupying. And that's what you can do with size of. Again, this means it's less common. It's you should not use it as pervasively as it's used in C, but it can be useful, especially if you're trying to replicate some particular data structure, a variance safe, very compact data structure that is reusing bytes of memory. Then you want to use size of to properly interpret your bunch of bytes, because that cannot be expressed as nicely. It cannot be expressed otherwise in the Zig type system. I've seen examples of this, for example. So these are also reasonable but advanced ways of dealing with memory, and that's where size of comes into play. Another one was source, src. So source, it's very, very nice. It's built-in that allows you to it basically tells you which line and number you are in, and you can use it to do some error reporting, to implement your own stack trace type of stuff. And again, not something that everybody should use all the time, but there is this moment where you say, oh man, I really wish I could tell myself where I am failing rather than just like faulting. Well, src allows you to do that. The final one of this list was field parent pointer, and man, field parent pointer is another one that really deserves its own dedicated talk. So field parent pointer is, I don't know, I think it's also in C. Maybe chat can tell me if this is something, if it's something that C also has. I guess it does, but I'm not 100% sure. And this is a technique that I first learned about in Zig rather than anywhere else. So field parent pointer looks very innocuous, and it's just a way of saying, well, I have a struct, and I have and this struct has maybe 3 fields, and I want, just given a pointer to given a pointer to a field, I want to know where the struct begins. So structs have a maybe because if it's not a packed struct, maybe you don't know how much size the struct has and what is the actual order in memory of the fields. But even though you might not know those, once those are defined, those are what they are in the full executable. They never change. So if you have this struct with these 3 fields and you have a pointer to the 3rd field and you want to know when the struct begins, you can do that. It's a little bit of math that the compiler can do very easily for you using this built-in. In C, you do arithmetic with offset of, usually. Thank you. So you can do that also in C. So here's, though, one interesting higher level construct that is used in some situations in Zig. And again, this really would deserve its own presentation, but something that kind of surprised me because I've never seen it done before. What you can do with this thing is, if you have a list where you have nodes, and inside the node you only put a pointer to a field of a struct, normally if you're doing like Python or Java, if you decide to put inside your node system pointer references to a particular property of another class, you have no way of accessing what else is inside that class instance, because you're kind of making the mistake, given what your intent is, of putting something that is too narrow inside your node system, right? You're putting a pointer to a field of a full struct, of a full class. And so what you would have to do is put a pointer to the entire class itself, I guess, rather than a pointer of just the field. But in Zig, and I guess also in C, if you know that that's a pointer to just a field of a struct, you can still access the rest of the struct by using this little bit of math, and sometimes it can be surprisingly useful, and that's how runtime interfaces are currently implemented in Zig, which again, it's one way of doing interfaces, I guess, with its own set of pros and cons. And it requires its own talk, I guess, to be fully explained. But this field parent pointer thing is a very interesting piece of functionality that looks very innocuous when you're just reading the description, but has very, very clever. It enables very clever usage patterns. So with this, we've seen 91 out of 102 built-ins, and I think we are getting close to the final one. Yes, that's the final one. Metaprogramming. Man, metaprogramming. So, we see call. So I mentioned call earlier. A call is the function that allows you, it's the built-in that allows you to call a function with a list of arguments when you have the arguments, again, as some kind of list. Field, hasDecl, hasField. These are three interesting things for composite types, so basically structs and unions. And I think also enums, maybe. So let's take a look at what field, hasDecl, and hasField do. So the first one is field. Field. I thought I clicked it. So field basically performs field access by a compile time string. So sometimes you say, you're doing some kind of metaprogramming thing where you know a field name because it's given to you as a string, and you would like to access that field, but you have a string and you don't have the symbol, right? And you would have to write it, and that's what field gives you. So this allows you to access field X and field Y inside of struct P, and these are strings that can be passed around as parameters. That's interesting. So can be useful sometimes. Then we have hasDecl. hasDecl, I think it's around here. Yep. hasDecl returns true if a given type has the given declaration. Keep in mind, hasDecl and hasField are very different. Well, actually not. They are similar, but you might sometimes wrongly use one in place of the other. So hasDecl gives you declarations. So these are declarations when these are function names or variables that are declared inside a struct acting basically as a namespace. While properties or fields are these things, the things that change from instance to instance of a given struct. So hasDecl works correctly for blah and high, but it doesn't work for fields. So this will return false because there is no nope var in here. There's a nope field, yes, but that's different. So when is hasDecl useful? When you're doing metaprogramming and you're accepting for example, an any type or a user provided type that is supposed to have a particular quote unquote interface, a particular comp time interface, a particular it should expose a set of methods, right? And And you can duck type your way around the shape of what you're given by using hasDecl. So for example, in my Redis client, I allow the user to override or to, I basically I have a way in my Redis client to delegate the serialization and deserialization steps of a particular type to the user if they have defined their own type that wants to decode or serialize itself correct. It knows how to do that correctly. So what I do is that I check if the type that I'm being passed in has a particular declaration. It's basically I have like a redis.parser, I think I don't remember, redis.parser, redis.serializer, I guess. These are the names that I chose. And if that type that I'm given doesn't have those, I use the normal procedure. Otherwise, I call into their functions, because by using hasDecl, I can check that those functions are actually there. Now, this doesn't tell me necessarily that the functions that have these names do what I expect them to do, right? But if you namespace stuff in a reasonable way, you can have a reasonable assurance that you are not randomly hooking into functions that were supposed to have a different meaning, which is useful. For example, in my case, as I said, I have people have to write const redis equals struct, and inside there they have to write const parser equals struct, and inside there they have to define the parse method. So they have so I only try to hook into stuff that is very reasonably meant to be for me, because I try to avoid collisions that way. But anyway, so these are very useful for this reason. So hasField, as we said, same thing except for fields of proper fields of a structure or union or enum. So that's nice. Next, we have tag type, these type info type name type of. Okay, so let's take a look at this. This is of all of these built-ins, I guess this is the one that is used the most. So in Zig, when you're creating a generic type, there is no concept of generic struct in Zig, or at least not there's structs that can have any type field, but that's a different story, and we'll not cover it. But like when you normally think of a generic struct, what you do in Zig is you have a function that returns a type, optionally can take in a type as an argument, or even anything else. It doesn't have to be a type. And it returns, since it returns a type, it returns a new struct definition. So in this case, this is a generic list, and it's a function that takes in the argument type, right? The thing that we want to put inside our list, the payload type, and it returns a definition of this thing that basically specializes around this type that you're giving in. So at this is a way of referring to your own concrete implementation of this struct definition here. We could not use, because otherwise we don't have a way of referring to ourselves in here, for example, for methods that accept a pointer to ourselves. So this is what this provides you. And that's pretty much it. So it's metaprogramming, but I think it's the metaprogramming type of things that we do more easily without thinking too much about it. Type and type info and type of. So let's start with type of and then move into type and type info. So type of, you give me a variable and you give to it a variable, and it returns you the type of that variable. This isn't really surprising. I think a lot of other programming languages have this system. What's important is that if you remember in the beginning, I mentioned, well, you know what? Let's talk about this later. I have it in a slide later. So type of just returns you the type of an expression that you pass to it. Type and type info, right? So type, or I guess maybe let's start with type info. So sometimes you want to introspect a type and reason about it at comp time. So if you do type info of a type info returns you a instance of this built-in type info definition that describes the type that you are looking at. So let's actually take a look at that. So source code, remember from the last talk, it's very easy to go to the standard library. So we have it in here, lib, std, built in. Is this stuff defined in here? I think it is. Type info, pubconst type info. I could have searched for pubconst or even pubconst type info, right? Because we were told, well, here we see that it's inside the built-in package, but you know that it's either defined in here or it is rewired in here in the main built-in file. It might be fully defined inside the built-in folder, but it's always wired into the main file anyway. So type info tells you if what you're looking at is another type definition, or it's a void, or it's a bool. No return, it's another peculiar type. It's an integer, it's a float, it's a pointer, it's an array, it's a struct. So let's take a look at int, for example. Ints tell you if they are signed and how many bits they take. Float tells you how many bits it occupies. Pointer tells you if we know the size, and there are different types of sizes, right? Either one, many, it's a slice, or it's a C pointer. We know also if the type that we're looking at is a const or it's volatile. So it allows you to check all these properties in the instance of type info that you're given and like switch over them and do a bunch of metaprogramming stuff based on the type that you're given. This is what I'm using extensively in my Redis client to basically have the Redis client decode a reply from Redis in the right way. One example of this, when I'm doing a non-one-to-one, non-obvious mapping, for example, there are some commands in Redis that return you a string, but if the user is asking for a number, I will try to do the number parsing directly for them so that they don't have to prepare a buffer for the string and then waste a bunch of memory that is not needed because I could read directly that stuff from the stream. So type info is very interesting, and it works well in combination with type. Type is the inverse operation. You give to it a type info description, well, an instance of a type info, and it returns you a actual type as you were defining, as your definition was. So for example, if you're implementing a, I don't know, power of 2 function, and the user can give you whatever number they want with also whatever type, it would make sense for you to say, well, my return type, if you're passing in a signed integer, my return type is going to be a unsigned integer because the power of 2 or normal numbers, it's always positive. Again, normal numbers. So that's useful stuff that you can do. And actually, you can see this happen in the standard library, in the implementation of this function in the standard library. I think they probably have a easier way than with type info, but I might be wrong. Maybe they are doing it with type info. There used to be different ways of doing this. So you know what? Let's take a look. I think it's inside math. I don't think it's defined in the main file, but I might be wrong. So let's take a look. Pow. Pow. Let's take a, do we have pow2 here? Pow2? No, we don't. Oh, that's a shame. What pow do we have? Oh, you know what? I think pow2 is defined maybe in the main file. Or maybe it wasn't pow, it was something else. I remember reading this stuff in here a long time ago. Let's see. Pow2? No, we don't. Oh, but was it square root? I think maybe it was the square root. So I'll go check out square root. If I don't find it, I'll just move forward. I think it was an interesting example of this being used actually in the standard library itself. So square root. There we go. So so you can see that square root takes in an any type, and the return type is based on thinking of inspecting the type that is being passed in. So let's take a look at what square root does. This is what defines the return type. But yeah, it does switch over type info. So returns the return type that s square t will return when given an operand of type t. So what it does, it says, well, are you asking me to do the square root of a integer? Okay. Then what I'm going to return is if you're giving me an integer, I will return an integer that is unsigned, even regardless of what the signedness of the integer type that you're giving me in, and with the half the number of bits. That's, I think, really clever, right? That's because this is something that makes sense for the based on what the square root function does, basically. So maybe this example might look like an overspecialization for you when writing normal code. I don't know, but yeah, it's one example of when these things can come into play. And also, this is also an example of how in Zig you can call functions to decide the return type. So this function gets called, and the return type of this function, which is a type, ends up being the return type of this function, which is another interesting meta programming thing that you can do in Zig. Not so much in other languages. I think so all of them. So since type info and type are the two most interesting ones, I have just a couple of final slides to properly underline how they work. So type info, in a sense, is like a distributor where you put in money and you get a soda back, right? While type is a distributor where you put in a soda and you get money back. So they are one the inverse of the other. As of today, type cannot produce any possible type. But I think I mentioned this already. But you can like I think the only limit that you have is that you cannot add declarations to structs, for example. But everything else you can do. And there's an open proposal for this. Oh, and I didn't show you the slides because I am a moron and I didn't change the the scene. So type info is the soda distributor. Type is the money distributor, I guess, that accepts sodas, which is an interesting concept. Okay, end of the presentation. A couple of trivia things, and then we can call it a day. So when do built-ins not behave like normal functions? For example, when using type gives you the type of the expression that you put inside, but the expression put inside is not really a run. It's just analyze for the return type. So this is something that I've done myself. Something that I done myself also in my client, because at one point I wanted to, allocate a bunch of async frames. But the problem with async frames, so you know that a function has a corresponding frames, which is the memory that is required to run that function. And we mentioned that earlier. And the problem is that if your function is generic, so it accepts comp time parameters like a type, how much memory actually you end up using for your function depends for each concrete specialization of that function, because maybe one function takes a small type and then requires less memory, another function takes a bigger type and then requires more memory. So when you have a generic function, you cannot get a frame out of a generic function. You need to fix in the function itself all the comp time parameters. And that's what I was doing when doing this. In my example, there were comp time parameters, right, that you had to pass in. So I was passing in all the comp time parameters, and this would return to me the right frame type. But it might look confusing, because if you're just thinking of these as normal functions, you know that usually the arguments get resolved fully, get executed first, and then the result of executing this is the argument passed to the outer function. But these are not functions. The R's are a bit peculiar. So in this case, the argument is only inspected to extract the return type and not actually run. Shouldn't this be type of? Oh yes, you're right. Thank you, Zakus. Yes, this is a bug in my slides. Yes, that's type of. Sorry. Um, so before reaching this, so talking about trivia, you're also able to do things like t.len. So if you had a type that was an array, you could also do .len on it to get the length. Also, optionals had a .child thing that allowed you to inspect the child. But apparently, Alex was telling me today those have been removed. I don't know, just an interesting piece of trivia. I think they were nice, but I also get why we might not want to have like multiple independent ways of doing the same thing. But that said, I think that uh, maybe a nice way of, I don't know. Anyway, yeah, and it should be changes, not changes, chances. God damn it! Yeah, you found two errors at the end of the presentation. By the way, this makes sense. The more you get to the end of the presentation, and more tired I was when writing the slide. Anyway, so there is another slide of spooky stuff, which I won't go over to. I'm gonna change the slide immediately. But if you, I don't know, you can maybe grab a screenshot of it from the video if you want to get spooked. So I guess that's the end of my presentation. This was another super beefy presentation. I apologize, but with this, I think we went through the main things that people might want to know about how to approach stuff in Zig after the standard library and this. And I think, next time is gonna be the release party, so I won't have to prepare a presentation. And but after that, I think I'll try to go back to shorter formats. I think having these become like a part 1, part 2 would otherwise be a bit boring. It's best to just get through one and that's it. Yeah, did we cover all built-ins? We did. We covered all 102 of them. And actually, the hardest part of preparing this presentation was actually double checking that I didn't forget anything. And I that's why there is a count at the top, because it was actually something that I was using myself to make sure I didn't miss anything. And yes, when I got to the end, the number did not add up. So I had to double check everything and strike out every single function, every single built-in that I mentioned in all the slides to find out which I missed. And by the way, one that really tripped me was CLZ and CTZ for some reason. Also, you know what? Let me tell you the final evil thing that I hope we can get fixed sooner or later. These are mostly in alphabetic order, but not exactly. They kind of are, except when they are not. They tend to be, so you tend to have A's up here, but then you have C down here. So you have a CLZ here, then, well, this is correct, I guess. But there's a bunch that are, for some reason, not alphabetically ordered. I mean, it's not completely without any meaning, right? Here you have all the math ones. You also have seal there, but I don't know. And then you have trunc and truncate. One is for floats. One is for integers. Anyway, yeah. So this was it. Is there any questions? I'm gonna give people a little bit of time to come up with questions, and otherwise I'll move forward. So what's the difference between using mul add versus doing A times B plus C? Wouldn't the compiler generate the same code at the end of the day? Good question. Let's take a look at what the documentation says about mul add. So mul add fuses multiply add similar to A times B plus C, except only rounds ones and is thus more accurate, supports floats and vectors of floats. So I guess the documentation this time gives a pretty good answer for this. Only one rounding step. That's cool. Let me see if there is anything else, but I think I really covered all the interesting ones. Any other question? Let's see if I'm missing anything on the other platforms. I think we're fine. So, yeah, I think that was pretty much it then, I guess. let me give you some spoilers. Well, I mean, I already spoiled it multiple times. So what about new stack call? Do we have a new stack call? There is no new stack call. Should we have a new stack call? We add new stack call? Maybe we should. What about the interfaces? Only we had some type of vtable type, huh? Anyway, let's move forward. So spoilers, there are not actually spoilers because I said that already. Have the release party next time. So join the release party, and we're gonna have Andrew. We're gonna take a look at the change logs. We're gonna answer questions. We're gonna have some fun. If you have funny artwork that you want to be featured, this is a good moment to send it to me so I can edit there. Oh, there's a question from Frank. Can you clarify what's the difference between built-ins and std.meta? So std.meta, it's a bunch of functions that make it easier for you to do what you're doing with the built-ins. They basically use the built-ins for you. But it's all userland code that uses what's in the built-ins. Another thing that maybe is partially related to what you are also saying. Also some of the types that the built-ins take as input or return as output, like the type info definition, is inside the built-in Zig file in the standard library. But I think these APIs are not yet 100% defined. So, for example, there have been discussions recently about adding more, making it easier for people to type check generic arguments. So right now we have that you can accept a normal argument of a specific type, a type argument, which is basically a normal type of a specific type. But then you have any type that kind of fuses the two concepts and doesn't have any restriction based on it. But then you normally, most of the time, when you accept any type, you're not really able to do everything with any type. You have a range of types that you know what to do with, and some others that you don't want. So, for example, we looked at the square root function, and the square root function can only do stuff with numbers. It doesn't make sense if you pass a string to it. So there is this proposal about seeing if we can extend the syntax of any type a little bit to provide in the signature some more information about what are the actual types that we are fine with. But anyway, that's just a proposal. But this kind of plays into the problem of how do we express constraints over types. And for example, this is probably some functionality that should go inside meta. You use meta to inspect. It makes sense also to use something in meta to express constraints. But again, constraints at the end of the day will be just code that plays around with types and type info. But it might make sense to provide a higher level API for those. As for the difference between meta.vector, honestly, for vector specifically, I'm sorry. Oh no, okay, that was the answer from Alex. So yeah, it's just, I guess, a higher level API. Another example is all the functions with overflow. Those report overflows correctly. They don't, you do get the information back whether an overflow has happened or not. But the interface inside the standard library is more idiomatic. It returns you a error with a name, which is, it's, how can I say, it's less error prone. Yeah, as I said, it's more idiomatic. So I guess this is more or less the philosophy between the built-in and their corresponding functions in standard library: more idiomatic API and or higher level functions. Yeah, release party next showtime. Don't miss it. You probably want to be here live instead of just catching up with the video on YouTube, because then you get a chance to ask questions about, I don't know, what's happening with the new release of Zig, or I guess whatever other question comes to mind to Andrew. So, yep, don't miss it. And with this, I think it's finally time for me to call it a day. So Thank you again very much. Please take a look at the YouTube channel, subscribe, slap the bell button, take a look at the newsletter, and if you want to chat with other people during showtime and stuff, take a look at the Discord server. So, bye-bye.